Hello, everyone, and welcome to Precalculus. This is section 5.2, verifying trigonometric identities. So we're already up to problem 13. 1 through 7 are on video A, and 8 through 12 you were supposed to practice on your own. So now we're on 13. At first glance, sometimes people think that these are a little bit harder, but they actually are pretty straightforward if you love to factor. So don't forget about factoring out. So I can take out a tangent squared x from both of these terms, and I'm left with secant squared x minus 1. Don't forget to hold that place. Whenever you see a square and a 1, you should be thinking about your Pythagorean identities. So the original identity is listed as 1 plus tangent squared is equal to secant squared, but of course it can be rearranged, subtracting 1 from both sides, which you can't do in the middle of a problem, but you can know this identity. So you have two choices. One is to know this fact and simply substitute it in as tangent. Secant squared x minus 1 is tangent. But if you only have the main identity written down, or it's all you can remember, you can just replace secant squared with 1 plus tangent squared x, and then the minus 1, and then you'll see right away that it's equal to tangent. So whether or not you have this second step is really up to you. And then, of course, that gives me tangent to the fourth x. I'm going to go ahead and write it also on the other side. And there you have it. We'll do one more just like that. Number 14. So because there's already parentheses there, people want to distribute the sign. But like the last time, it's actually going to be easier if we factor. I'm trying to get a cosine to the fourth, so I'm going to take the cosine to the fourth out. Oops, forgot my S there. So I'm going to take out my cosine to the fourth, and that's going to leave me with 1 minus cosine squared x times sine of x, which gives me cosine to the fourth x times, again, another Pythagorean identity, sine squared plus cosine squared is equal to 1. So 1 minus cosine squared is sine squared. And then if you have sine times sine squared, you have sine cubed, which I can put out in the front because of the commutative property for multiplication. I'm going to write both sides to show that I've finished, and I got them to be equal to each other. So when people first see these, they think that they're harder. Your book actually puts them at the end as if they're the challenge problems, but once you got the hang of factoring, these are pretty straightforward. There are 4 more to practice on, and you can give those a try on your own, but I'm going to work on doing some different kinds of problems. So these are even problems from your book in case you need to see a few worked out. So as soon as I see 2 things on one side but only 1 thing on the other side, I'm always thinking to myself, common denominator, because I need to get 2 things to become 1 thing. So I'm going to switch this to tangent of x on the top and tangent of x on the bottom. That gives me 1 over tangent x plus, and this is going to give me a tangent squared on top over tangent of x. Since they have a common denominator, I can write them as a single fraction. And 1 plus tangent of x is secant squared x. So it's all about getting a common denominator, and you should do that whenever you see 2 things have somehow miraculously been put into 1 thing. That happens by common denominator. And of course, know your identities. So this has a mix of secants and cosines and sines and tangents. So one of my strategies is to change everything to sines and cosines. So this is 1 over cosine minus cosine. And this is sine theta times sine theta over cosine theta. So this side is sine squared theta over cosine of theta. This side has no signs. The only way to change a sine into a cosine is if it's squared. So since I do have it squared, I can change that to 1 minus cosine squared theta. I can actually keep working on this side if I want to. I can separate this into two separate fractions. We don't do this very often. Normally we're so keen on getting a common denominator. But in this case, I'm going to separate it out from my common denominator. And then that gives me 1 over cosine of theta minus, and then I have two cosines on top and one on the bottom, cosine of theta. And I'm done. So I didn't really mean to work on the right, but as I was going through, it just seemed easier. My original plan was actually, so I'm going to put this in a big or, you're not required to do both. My original plan was just to get a common denominator. So I was going to multiply this one on the top and the bottom by cosine of theta. That would have given me cosine squared theta over cosine of theta. And then once I had a common denominator, I was going to put them together, and then I was going to change that to sine, which was the step that I had achieved up there. So, so many choices for how to do these, but this green one is an or. Number 3. So this uses a little used identity that I want to make sure I review. Sine of negative theta is the same as negative sine theta. Cosine of theta, negative theta, is positive cosine theta. And tangent of negative theta is negative tangent theta. So if you forgot those, they do come up. Unfortunately, not that frequently, so people don't have them memorized. But honestly, you shouldn't really need to have them memorized. Remember the reason for it, and it'll be easy. Think of this as meaning you have a quadrant 4 angle. So positive theta moves in this direction, but negative theta moves in this direction. But when you move in this direction, cosine doesn't matter. It's sine, rather. It doesn't matter because cosine is positive in quadrant 4. So cosine of negative theta is actually going to give you the same answer as cosine theta. But since sine and tangent are negative in quadrant 4, or even if you were to go all the way around to quadrant 3, it would still, this would work. So right away, I'm going to replace this with 1 minus sine of y. But I don't want you to think I'm just pulling the sine out because it won't work for cosine. I'm just doing it because it's sine. I draw my line. And then I see a cosine squared. I can change that side or I can FOIL. First, outer inners cancel, minus sine squared y, and that simply is cosine squared y. Or if you're not really good at recognizing that yet, remember that 1 is sine squared plus cosine squared. You can always make your replacement that way if you feel more comfortable doing it. But you can skip this step with the red crossouts. 1 minus sine is cosine squared y. And on the other side, cosine squared y. Number 4 has a lot going on in it. It has a mix of cosines and cotangents, and often I will change my cotangents to sines and cosines, but it's also in a fraction, which would give me a complex fraction. And then I have a 1 minus sine, which when I see that, I often think I might have to do the conjugate. I have 2 terms suddenly becoming only 1 term, which means I think I'm going to need a common denominator. There is definitely a lot going on in this problem. So I think I'm going to start by taking care of that conjugate. I feel pretty confident that that would be a good start. I don't actually already have this problem worked out, so maybe it won't work. But that's also good because that's how some of your problems are going to be. You're going to be going along doing a problem, and it may or may not turn out the way you want it to. So cosine of x times cotangent of x, don't forget that minus 1 there, And then I'm going to go ahead and multiply this first, and then my outers and my inners cancel. That's why I chose the conjugate, minus sine squared x. And then I can change this to cosine. I'm actually not going to distribute this. I'm going to leave this where it is, because I think with my cosine squared on the bottom, I'll cancel that one on the top. And on the bottom, I get cosine squared x. So now I'm going to get rid of one of those and one of those. And when I go to rewrite this, I'm actually going to do another step at the same time. You can combine some steps, and that is I'm going to separate out my cotangent. So this is an important concept here. If you were multiplying, you would go straight across the top and straight across the bottom. So this one does not also get a cosine. That would only be if you were adding them. So when you have two things that are being added, like if I were to separate this one now, it would be 1 over cosine plus sine of x over cosine of x. That's how that one would separate. But when you're just separating multiplication, one of them gets that denominator and the other one can just have a 1. And if you remultiply that, you'll see that that works. So the reason that I separated it out, I've got my eraser, I'm just going to fix that little x there. The reason I separated it out is because I wanted to change cotangent to cosine over sine. And I thought that if I did it here as part of the complex fraction, I might lose some people. So I thought I'll separate it out first, and that way I can make it into a fraction. And that actually worked out really nice, because now I have the cosines canceling. And when I remultiply, the numerator this is just a 1 now. So 1 plus sine of x over, and then that cosine's gone, over sine of x. So this becomes, I'm going to separate it into two separate fractions. 1 over sine of x plus sine of x over sine of x gives me cosecant of x plus 1. And I think to myself, hold on, what was I trying to get? Just cosecant of x. All right, this is where somebody might be really tempted to fudge it, or maybe check the original problem. But it turns out for me, I just lost this minus 1, minus 1, minus 1, minus 1, minus 1. A very long problem. And fortunately, with that minus 1 there, the final answer is, a little more room there, cosecant of x. So don't give up if it doesn't work. It's possible you made a mistake along the way. And then the other side is also cosecant of x. That was a hard one. They're getting harder. No, and this one doesn't look so great either. And what makes this one new and interesting is I've mixed tangent of x and tangent of y. So those of you that have been a little lazy about writing your x's and your thetas and things, this is why you need to have them, because they're not always the same angle. Oh, so where to even start? Well, I guess I would start by trying to make all either tangents or cotangents. So I am going to get I'm going to flip this to 1 over tangent of x plus 1 over tangent of y. And then this would be 1 over tangent of x times 1 over tangent of y minus 1. And then I'm going to get a common denominator. So this one needs, notice I'm showing my work. That's what I want to see from you. And this one needs a tangent of y. Having another color really helps. So that numerator is now a complex fraction. I realize that. Tangent of y, switching pens, tangent of y plus tangent of x all over tangent of x times tangent of y. I don't know if this is helping, but I certainly like having that tangent of y plus tangent of x because I see that on the other side. Now, the only way to make these two things go together is if I give this one also the same denominator. So tangent of x, tangent of y, and tangent of x, tangent of y. Because technically this is one thing, multiplying the numerator times the numerator, denominator times denominator. So now I have 1 minus tangent of x, tangent of y, all over tangent of x, tangent of y. So try not to be overwhelmed. Just make the top into a single fraction, and then make this bottom into a single fraction. And maybe the way I wrote it wasn't the easiest for you, putting these separately. You can right off the bat, when you're doing this one, you can think of it as it's a single unit there. It can stay a single unit if that helps you. So I'm giving these to a common denominator. The reason I wanted to do that is because now I can keep that first one. I can change, see this division? I'm going to change that to multiplication, and I'm going to flip this one. So I'm going to flip this tangent of x, tangent of y, over 1 minus tangent of x, tangent of y. That's how you deal with a complex fraction. When you have a fraction over a fraction, you keep the first one, you change it to multiplication, and you flip the second one. And then great things happened. This all canceled. And now when I go straight across the numerator, I get just tangent of x. Obviously, I'm going to reverse it because I'm trying to make it look like the other side. Plus tangent, sorry, so much pen trouble today. Tangent of y all over 1 minus, this times this is gone, tangent of x, tangent of y. Which is exactly what the other side was. It wasn't even as long as the last one, even though it looked much harder. Great job. So I am going to show something slightly alternative, and that is you don't have to use keep, change, flip. I can't undo that. Well, I guess I can. I'll just rewrite it. So this was tangent of x times tangent of y. So if this makes sense to you, what I would do is I would multiply the top and the bottom by something. As long as you multiply the same thing to the top and the bottom, you're just multiplying by 1 and it doesn't change it. What am I going to multiply by? I'm going to multiply the top by tangent of x, tangent of y, and the bottom by tangent of x, tangent of y. Then this cancels, and this cancels, and I'm just left with tangent of y plus tangent of x over 1 minus tangent of x, tangent of y. So that's alternative to what I had in the red before, if you wanted to try that. Okay, last one. So it's really tempting for people to square both sides. Do not do that, okay? Do not square both sides. You can't do anything to both sides. You can't add to both sides, subtract from both sides, and you definitely can't square both sides. So I'm going to put a line there to show that. So how does a square root disappear? Well, what you can do is you can make a perfect square underneath the radical. The square root of x squared is just x. That's how a square root disappears. It actually is the absolute value of x. Because let's say that x is 3, then the square root of 3 squared is the square root of 9, which is 3. But if x is negative 3, then the square root of negative 3 squared is the square root of 9, which is 3. So see how that ended up becoming positive because we squared it? So this is the fact that you need to know. So what I'm going to do is I'm going to take this square root, 1 minus cosine of x over 1 plus cosine of x, and I'm going to give it another 1 minus cosine of x, because if there's 2 of them, then it'll make 1 minus cosine of x. But of course I have to do the same thing to the bottom that I do to the top. And that gives me 1 minus cosine of x, the quantity squared. And this gives me 1 minus cosine squared x. I'm actually going to FOIL it out. First, outers and inners cancel, and last times last is minus cosine squared x. And then I'm going to leave this numerator the same. And the denominator, hopefully by now you recognize 1 minus cosine squared is sine squared. And as a final step, this is a perfect square. So 1 minus cosine of x. And then sine squared x is just going to become sine. But like x squared, I am going to put it in absolute values. So this one doesn't need the absolute value because cosine never is bigger than 1. So you don't have to worry about it. Do you remember that the graph of cosine starts at 1 and it never goes above 1? So that's definitely going to come out to be positive either way. So it looked hard with that square root, but it's not. All right, keep practicing these and have a great day.